Hello everyone, I hope you are doing well. In this video we are going to solve problem 13 from chapter 7 of Introduction to Statistical Mechanics by Roger Bowley. The chapter name is Maxwell Distribution of Molecular Speeds. Yes, and it is problem number 13. Let's see the problem statement and then we'll dive into the solution. Here you can see the problem number 13. It says calculate the Maxwell Botlzmann distribution and average speed of free particles in two dimensions. So we need to find out Maxwell Botlzmann distribution function, okay, in two dimensions for a free particle, and in addition to this we have to find out average speed of that free particle in two dimensions. So it's one of the derivation type of thing that we have to do for a free particle in two dimensions. If we look at the topics that are being done on the chapter, you'll see the Maxwell-Boltzmann distribution function has been derived for a 3D case. In addition to that, RMS and average speeds were also derived based on a free particle case in 3 dimensions. So what we have to do in a different way is to do the same derivation but considering the 2-dimensional case. And the method that I'll explain to you people is so simple that will introduce to you a general method framework that you can use to derive for 1D case as well, and you can derive it for 3D case also. Okay, so stay tuned and let's start. Maxwell-Boltzmann distribution function tells us that how many particles would occupy states in the interval k and k plus dk. Okay, so we have some interval here and this function tells us that how many particles will occupy the states that are available between k and k plus dk. Since we are considering the availability of the states, then we are talking about density of states in turn, so it's related to density of states as well. Now let me write in general the total number of particles that can occupy states E of k in the interval k and k plus dk such that there are d of k dk density of states available in k and k plus dk interval. The function is given by the Maxwell-Boltzmann function is given by this expression. In k space, we'll convert it into speed space when we need to find out the average speed or something like that. We'll do that step later on. So this function gives us the total number of particles that can occupy a state in this interval. Okay, and in principle, if you want to find out the interval, then this is the upper point of interval and this is the lower point. Upper point minus lower point, it gives you the interval length, which is dk. Okay, we are just taking differential intervals. And now let us write the formula, and this formula is n. N shows the total number of particles multiplied by the Boltzmann factor. Boltzmann factor, this is the Boltzmann factor, if you remember. This is Boltzmann factor that gives you the probability that a state E of k would be occupied. Okay, z is the partition function, and if you people remember, then the Boltzmann factor is actually the probability that a certain state would be occupied. Or let me write it without that. E by kt divided by z. This gives you the probability that the E state will be occupied by a particle. Okay, so this is simply this thing multiplied by n particles. Here we were considering a single particle, here we are considering capital N particle. That is why we are multiplying it with this. Okay, and I am telling you this, people, so that you may have that basic understanding that will help you to remember that formula. Okay, that is why I am telling you. So this gives the total probability, and that probability should be multiplied by the density of states, because we should keep in mind that what states are available. So this gives the total occupancy of states in the decay interval. Okay, this is the basic formula. Okay, and it is valid for 2D, 3D, 1D, or whatever case you are considering. For 3D case, for example, you will put another value of z and some other value of d of k. For 2D, z and d of k value will be different. For 1D, z and d of k value will be different. So density of state and partition function just changes. Okay, this is a general formula, and from this formula you can move onwards to whatever formula that you want to derive. Okay, this is the starting point. You can remember that formula very easily based on what I told you, people. Okay, and that's the correct description of the formula, as well as you can see the topic of the relevant topic in the book as well for confirmation. Now let's proceed for for a 2D case. For a particle, for a free particle, you write for a free particle in 2D, we have, for a free particle in 2D, you have z equals to a by lambda d square. Lambda d is the de Broglie wavelength, and the reference to this thing could be found in chapter 5. Okay, when you are considering a free particle in 1 dimension, a free particle in 3 dimensions. So you are studying the thermodynamics of a free particle in a cube, which means in 3D, in a 1D case as well. So you will see how lambda d appears. Okay, I have also uploaded a video on those topics, so you can visit those videos if you want to have that background, but that's not relevant. Do it if you are interested. So z equals a over lambda d square. Now let me and d of k, density of states in 2D, is ak by 2 pi. These are the values that you will be using. Now let me clarify one thing. If it is density of states, if it is a 3D case, okay, if it is a 3D case, you will take z, that is partition function, to be equals to volume divided by lambda d cube. Okay, if it is a 3D case. If it is a 2D case, you will take partition function for a free particle. Okay, for a free particle to be equals to a over lambda d square. If it is 2D, it's square here, it's a here, area, which is a 2D thing. And for 3D, it's cube here, it's v here. And for 1D, you will take L over lambda d. You can see the values and how they are changing from each other, you know. So you can remember it very easily. If an unseen problem comes in, then you can put simply z equals to L over lambda d if it is 1D case. If it is 3D case, put z equals v by lambda d cube. Okay, these are constants actually. So it's really easy. You have to use this method, that how I'm putting the values and how I'm integrating and all that stuff, but not exactly if it is a 1D case, for example, but the same way of treating it. Okay, you just have to put accordingly, values accordingly. You just have to put values accordingly, and you know the density of states formulas for 1D, 2D, and 3D case. For 1D, it is L over pi. Okay, for 2D, it is ak by 2 pi. For 3D, it is vk square by 2 pi square. Okay, so simple as that. So for a 2D case, I'm taking this and this. Now let me put these values right into this expression. 1 becomes, after putting these values, 1 becomes f of k dk. N is constant, so e to the power minus e by kbt. This is Boltzmann constant. Okay, by z is a by lambda d square, that comes in numerator. So d of k is ak by 2 pi dk. This a and a cancels out and we are left with n lambda d square. I'm writing the constants first by 2 pi in denominator, then k comes, then e to the power minus e by kbt dk comes. This is the Boltzmann this is the Maxwell-Boltzmann distribution for a 2D case. Okay, now let us convert it into a let us convert it into velocity terms, because we want to find out the average speed, so we should know how this formula looks like in velocity terms. Okay, this is the Maxwell-Boltzmann distribution function for a 2D case. Now let's convert it into velocity space. And for a non-relativistic particle, you write for a non-relativistic particle we have p is equals to mv, simply, as we know about momentum. So, and we also know that p is equals to h cut k as well. So that is equals to, in quantum mechanics, so that is equals to mv, and we want to find value of k, that would be mv by h cut. Okay, we simply have to put the value of k from this equation to an equation that I'll tell you, people, but yes, this is the expression of k that will help us to convert. Now f of u du, if you want f of u du, okay, that should be equals to f of k dk, but you want f of u first. For that purpose, what I'll do is taking du in this side of equation. Okay, I'm giving you a method to write these things in differential forms. Okay, so but we need distribution in some du interval, so we'll multiply again on both sides du. Okay, this is differentiation that we have to perform. Multiply by f of k, that is already known, du remains the same, so let us call it as equation number 2. We should know dk by du. Here it is. We can take differential of both sides, so m by h cut is constant, so differential applies on v, so it is dv. Okay, dk is equals to m h cut m by h cut dv. You can take dv right in this side of equation, so that dk by dv is equals to m by h cut. Some other simple method is to take differentiation with respect to v on both sides. So d by dv, m by h cut comes out of the differentiation, and dv by dv is 1. So both of these methods are same. I hope you got it, what I was saying. Sometimes I say things in a difficult way, but never mind. F of u du, let us put the value of f of k, which is here. It is n lambda d square k by 2 by e to the power minus e by kbt, then dk. So dk by du, we know that it is equals to m by h cut. I'll put here, then dk will not come here because we are putting value of f of k, and value of f of k f of k dk. We can cancel dk on both sides, so this is actually f of k. Other than dk, the thing is, so we'll not write dk here. All right, so be mindful of this thing. And here it is k, we need to remove it and convert it into v. So we know that the value of k was k equals mv by h cut, so we'll simply put here. Let us do that. N lambda d square by 2 pi, k is mv by h cut, e to the power minus e by k bt, m by h cut dv. Okay, u or v, whatever notation you want to have for speed. So m and m is m square, h and h cut, these two are h cut square, v e to the power minus e by k bt dv. Now this e should be converted into speed as well, because we know that we used to write this, and I stopped writing it like that because I was trying to reduce complexities in what I'm writing so that you people may understand its energy, and that is why. So we should put the value of E here as well, which is actually kinetic energy, and we know that it is equals to 1/2 mv square. For a non-relativistic particle, we'll simply put 1/2 mv square here, n lambda d square, let me write it here, n lambda d square by 2 pi h cut square m square v e to the power minus, in place of e we'll write it's simply mv square by 2 na. Okay, e by kbt we have, so we'll divide kbt on both sides. So in place of e by kbt we'll write mv square by 2 kbt, so it's mv square by 2 kbt dv, f of v dv. Okay, this is the Maxwell-Botlzmann distribution function in speed form. Okay, now this function will be used to derive the average speed, because we wanted speed, that is why we wanted to express it in terms of speed. Now the average speed is given by, this is one part of the answer. Okay, this is one of the answer, and the other thing was average speed that we needed to calculate. Let us denote it by small v with a bar on it. So v bar would be equals to 0 to infinity. Okay, then we have this distribution function that we had, multiply by the variable whose average needs to be calculated and its speed, that is why we'll multiply it with speed. If you want to find out average kinetic energy, for example, then we'll use kinetic energy term here if we wanted to calculate average kinetic energy. So I was saying that it's a general formula that how you can write it for other averages as well. So I was wanting to find out the average speed, that is why this distribution function whole multiplied by the speed, because we want to find out the average speed, divided by 0 to infinity f of that distribution function only, no multiplication with speed. Okay, now let us put the values. Let me write this v here. Okay, then f of v dv, which is this whole thing. Okay, so this v and this v multiplies to become v square, 2 pi h cut square e to the power minus mv square by 2 kbt dv. Then in denominator we have 0 to infinity, this whole thing again, n lambda d square m square by 2 pi h cut square v e to the power minus mv square by 2 kbt dv. Now these are constants, so they will cancel out above and below. Okay, we write equal here where the bar is. Okay, where the division line is, we'll write equal right there. So these cancels out and we are left with these integrals. we have to solve this integral to find out the average speed. So okay, this is the expression so far. You can see here it's v square here and it's v here. Let us do some substitution that will reduce that integration into some standard form, and then we'll directly put some of the integrals direct values, and then we'll get, after that we'll get our final answer. So for that purpose, I'm letting this whole power, okay, I'm letting this whole power equals to, in power we have mv square by 2 kbt, not the negative sign, okay, only this term. Let us take it equals to x square v square x square, okay. So that v square is equals to 2 kbt by m x square. Taking under root on both sides, it gives the value of v. All right, and besides the value of v, we have here, we can see mv square by 2 kbt. We can simply put x square in place of that. In place of v square, we need to find out the value of v in terms of x for all these things that appear here. In place of these things, we'll write x square simply. In place of v square, we'll write these values. In place of v square, you'll write this. In place of v, you'll write this. In place of dv, what we are going to write, for that purpose we'll take differential of both sides. So this is constant, it will remain the same, and it's simply that. Limits of integration remains the same because they are directly related to each other and there is no difference at all. So the integral becomes v bar equals to 0 to infinity. In place of v square, you'll write this. It is 2 kbt by m x square e to the power minus x square, okay. In place of dv, you write this whole thing. It is under root 2 kbt by m dx, okay, divided by 0 to infinity. We had v in denominator, so 2 kbt by m, value of v is 2 kbt by m under root into x, then e to the power minus x square simply, and then the value of dv, which is under root 2 kbt by m dx, okay. These two cancels out above and below. This one comes out of the integral and this one as well, so we'll simplify them. 2 kbt by m whole power 1, and it's 2 kbt by m whole power 1 by 2. Under root is 1 by 2. It's in denominator. If we take it in the numerator, it is negative 1 by 2. And since both of these quantities are same, we can do this principle of exponential. 1 minus 1 by 2 will subtract the powers simply. It's 0 to infinity x square e to the power minus x square dx, then 0 to infinity x e to the power minus x square dx. Okay, now they are in standard form. We'll put the direct values, and before that let me write what comes here. 1 minus 1 by 2, if you take LCM, it's 1 by 2, okay. So here we are left with 1 by 2, so it's under root 1 by 2 is like under root, so I'm writing it like that, 2 kbt by m. Now the value of this integral, okay, is always under root pi by 4, and the value of this integral, this specific integral, is always 1 by 2. You can mention it separately that these integrals are standard and the values are equals to these, okay. So it's under root pi by 4 in the numerator, okay, and 1 by 2 in denominator. Since 2 is in the denominator of a denominator, it comes in numerator, so it's 2 here. 2 ones are 2, 2 twos are Okay, and this is under root pi, and we can do kbt by m dot under root pi by 2. So this is under root 2. I'm writing it separately. Then we have kbt by m. Since pi has under root as well, we can write them in single under root here. Okay, and we'll write 2 right here. Under root 2 by 2 is can be calculated like that. It's like this. Okay, and kbt pi by m, and if you simplify it, I'm taking this 2 1 by 2 in the denominator, so it's like that. Okay, 1 minus 1 by 2 is 1 by 2 power 1 by 2, so it's all in all under root 2, 1 over under root 2. And this same thing, we'll write all these quantities in single under root, so that we have pi kbt. I'm writing pi first, kbt divided by 2m. This is the average speed of a free particle, of a free non-relativistic particle in 2D. Okay, so this was the final formula, and you actually calculated, derived Maxwell-Botlzmann distribution function for a non-relativistic particle in 2D and their average speed as well. And that is the solution. Good luck for your exam.